Good morning, everybody. Welcome back to our study of stellar pulsations. In yesterday's lecture, we have considered small perturbations around a hydrostatic stellar model, and we have derived the equations governing or describing small spherically symmetric perturbations around the background model, means radial perturbations with spherical symmetry around the hydrostatic stellar model, or in other words, around the background model. We were left with linear equations. We have assumed that the perturbations are small, and as a result, we have obtained linear equations which are partial differential equations, both in the spatial variable taken to be the mass and the time as the second variable. Now, as these equations are linear and the coefficients did only depend on the background model, we were able to separate the time dependence in an exponential form, which left us then with an ordinary differential system of fourth order, but containing the time dependence as a free parameter, which we denoted by eigenfrequency or eigenvalue. So we are left with, after some manipulations which were done in order to enable a convenient numerical treatment of this system of equation, we were left with this fourth order ordinary differential system containing the eigenfrequency, which denotes the time dependence of our perturbations, and coefficients, which were dependent only on the spatial variable and contain, so to say, the information on our background model or on our hydrostatic model. So these coefficients, well, coefficients C1 to C3 and C4, together with the derivatives of the opacity and the equation of state. So this information about background model plus the eigenfrequency appearing here, these are the parameters of our differential system. A differential system needs for its complete solution boundary conditions or initial conditions, and we have asked ourselves what is a physically meaningful boundary condition, and we found out that we have actually two conditions which we have to take because the coefficients become singular at the center, and so for as a regularity conditions we have to adopt these two boundary conditions at the inner boundary, and we are not allowed to take any other boundary condition, because otherwise we would capture some diverging solution or contributions from diverging solutions which we, for physical reasons, cannot interpret. Diverging solutions are not physically interpretable, so we have to take these solutions once our model extends down to the very center of the star. At the surface of the star, at the photosphere, the boundary conditions are ambiguous because the boundary of our model is not the physical boundary of the star. And so these are ambiguous, and some reasonable boundary conditions consists of adopting Stefan Boltzmann's law, because the outer boundary is the photosphere. The linearized version of Stefan Boltzmann's law is L given by the Lagrangian displacement plus the temperature, and another condition would be to require a force-free boundary condition, which means that the Lagrangian pressure perturbation is zero there. Okay, now if we have done all this work, and we might ask ourselves, like a mathematician, can we solve this system? And well, a mathematician's answer would be no, you don't have a solution. So what a pity, we have done all this work and a mathematician comes and tells you there is no solution to your problem. Well, we have one addition, we have in our system, we have one parameter which is still not fixed here. This is the eigenfrequency, and the question arises whether we could adjust this eigenfrequency in a way to guarantee a solution. Then we would have done two things at once. We would have guaranteed the solution of our system, and the second one would be we know something about our eigenfrequency. It's still undetermined. Once we know our eigenfrequency, we know the time dependence or the time behavior of our system. So if this could be done together, this would be quite nice. We guarantee that we have a solution. This is what would be one thing. And the second one, we get some information about our eigenfrequency. Okay, so, well, let's consider the solution problem of our system. Once we take all our conditions at either the inner or outer boundary, once we could do this, taking all four conditions either at the inner boundary or at the outer boundary, then we know that we always have a solution. This is a typical initial value problem, specifying all conditions at one boundary and then starting to integrate in a unique way from one boundary to somewhere else. The question or the problem here is that the boundary conditions are distributed between two boundaries, and in that case, in general, we do not have a solution. So there is a basic difference between an initial value problem for the same equations. We consider the same equations, but in one case, the boundary conditions are given all at one point. All four ones are at one point. You always have a solution. And if they are distributed between two different boundaries, then in general we will not have a solution. Well, to illustrate, this is a rather counterintuitive system here. And in order to illustrate the situation and how we proceed, the strategy of deriving eigenvalues, determining the eigenvalues, and at the same time guaranteeing the solutions of a solution of the problem, I would like to give you an example, a very simple example where everything can be done analytically. This can be done only numerically. And in that case, we may get an impression or get a feeling what's going on here, what solvability of the system means as a boundary eigenvalue problem, and how we determine then the eigenvalues at the same time as we guarantee that the system has a solution. The system which we had in mind was our analogon of the pulsating star, which is the organ pipe of length L, and we have considered which are the equations which govern small perturbations of the configuration of an organ pipe of length L, constant pressure, constant density within our organ pipe. It is similar to the star. It's a one-dimensional acoustic configuration. Our star is a one-dimensional configuration. The organ pipe is also a one-dimensional acoustic configuration. We choose independent Eulerian variables x and t. X is going along the length of the organ pipe, and time t, of course, is the second parameter. Well, we have then done Eulerian perturbations of the background configuration, which is very simple in that case. Everything is constant here. And we have considered first, of course, the mass, the perturbation of the mass conservation equation, which in this case gives the Eulerian derivative of the Eulerian perturbation of the density. A tilde means Eulerian perturbation, and we have the divergence of rho times v reduces to d by dx rho 0, which is the background, the the stationary density times the velocity perturbation. Similarly, we have perturbed the momentum equation. On the left-hand side, this is the acceleration. This is the perturbation of the pressure, and we have related then the pressure perturbation to the density perturbation. Differentiate this equation once with time, with respect to time, and in the end we are left with the typical one-dimensional acoustic wave equation, which tells us that the second time derivative of the velocity perturbation minus sound speed squared times this second spatial derivative of the velocity perturbation is 0. So this is concerning the spatial variables. Concerning the time variable, it's of second order that coincides with our stellar model. We have the acceleration in our perturbation equations, which gives a second order derivative with respect to time. So that seems to coincide both for the organ pipe and the spherically symmetric perturbation of the star. But here we have a second order spatial derivative, whereas in the full system, in the system describing radial pulsations of the star, we have a fourth order system. So what is different here? Which equations have not been considered here, which have been considered for our stellar configuration? Well, in the star we have considered mass conservation, momentum conservation, and energy conservation and energy transport. This has been disregarded here, and therefore we arrive at the second order system. But how did we deal with the thermodynamics here? We somehow got rid of the entire thermodynamics, but somewhere it must be hidden. So we have done something with the thermodynamics of the system. What did we do with the thermodynamic aspects of the problem for the organ pipe? Where is the thermodynamics? Where did it go? No thermodynamic equations here, no energy conservation, no energy transport. But somehow the system must at least take into account, in a certain sense, it must take into account the thermodynamics. Well, it enters here, where we relate the pressure perturbation to the density perturbation. In principle, I should have said something about how this derivative of pressure with respect to density should be taken. Well, what we did here, I did not specify which quantity needs to be kept constant here, because in general you have that, I block here. In general, the pressure is a function of density and temperature, or pressure may be written as a function of density and entropy and so on. So in principle, from a thermodynamic point of view, there has to be a second parameter. And here I have, without saying anything, I have taken the derivative of pressure with respect to density without considering the second dependence. Well, this can be realized either by saying, well, I keep the temperature constant or I keep the entropy constant. Then this derivative would have to be taken at constant temperature or constant entropy, and this means then this derivative, having constant entropy or constant temperature, would then correspond to the square of the isothermal sound speed or the adiabatic sound speed. Usually it's the adiabatic sound speed, because the changes of state within a sound wave are fast compared. The mechanical changes are fast compared to the thermal exchange of mass elements with its surroundings. So we have in some sense, we have hidden the entire thermodynamics in this relation between the pressure perturbation and the density perturbation. So it's not really abandoned, but it's hidden somewhere here in the derivation of this equation. Okay, so we have this one-dimensional acoustic wave equation, which should describe small perturbation within our organ pipe. Okay, here we are. Okay, like our stellar system, like our pulsating star, of course, we have to have boundary conditions for this equation. So we need two boundary conditions because this is an equation of second order in the spatial variables. Well, we have an organ pipe which extends from x equal to 0, it's the bottom boundary, to x equal L, which is the top boundary of our organ pipe. And well, if we confine our organ pipe with rigid walls, then a rigid wall would require that the velocity perturbation should be 0 there, because it cannot move. There is a rigid wall. Then the velocity perturbation should be 0 both at the bottom and the top boundary. We have the same situation as in our star. The boundary conditions are not given at one boundary, but they are distributed between the bottom boundary and the top boundary. Similar situation as in our star. If we put all the boundary conditions at one place, at x equals 0 or at x equal to L, we will always have a solution. But in the case when we distribute these boundary conditions between the two boundaries, there is likely to be no solution of the problem. Okay, we'll do also the same as we did with the time in our star. We separate the time dependence in the same way as we did it for our star. So we write that the Eulerian perturbation of velocity is given by some function which only contains the spatial dependence times an exponential in time containing some free parameter which we call, similar to our pulsating star, which we call the eigenfrequency omega in this time, in this place. So we write the time dependence as an exponential of I omega t. Well, why could we do this? Why does this lead to a solution? Here it is pretty obvious. Well, differentiation of the exponential gives the exponential times I omega, and here we have a second derivative with respect to time. This gives a minus omega squared, and all these functions contain the exponential, so we can cancel this exponential. But what is the requirement to do that? Is there a requirement on the sound speed? What would happen if one of the coefficients would depend on time? Then this separation is no longer possible. So one of the basic requirements to be able to separate the time is the independence of time of the coefficient of the differential equation. This was also true for our stellar system because all the coefficients were dependent on the background model, and the background model is time independent. So all the coefficients are independent of time, and that's the reason why we can separate out the time dependence here. Okay, so we did everything in analogy to our stellar pulsations: time separation, boundary conditions, separate or distributed between the two boundaries. So we have, as a result, we have a boundary eigenvalue problem. It's called a boundary eigenvalue problem containing a free parameter which can be adjusted to guarantee a solution. We have a boundary value problem because we have two boundaries at which the boundary conditions are given. And we may take the freedom in the eigenfrequency to guarantee a solution, and at the same time to determine for which values of omega we actually get a solution of the problem. Okay, now here we are in a nice situation that we have an analytical solution of the problem. So we have to solve this second order equation in the independent variable x, where all coefficients are constant. The sound speed is constant, and also, of course, omega is constant. So we have a second order equation with constant coefficients, and you all know the solution of a second order equation with constant coefficients. This is also an exponential. Okay, we'll come to that in a minute. Here is I have summarized what I already said. Well, for two boundary conditions at x equals 0 or x equal to L, we have an initial value problem solution exists for arbitrary omega. If they are distributed, then in general there is no solution, and we adjust now omega to enable a solution, and we have a boundary eigenvalue problem. So the solution of these second order equation with constant coefficient is an exponential, and we write it in the form v hat is proportional to exponential ikx. If we insert this into our equation, then we have minus omega squared. Of course, the v hat, the constant or the exponential can be eliminated simply because the exponential is contained in any of these terms, and the second derivative of the function xikx here with respect to x, this gives a factor ik squared, this derivative, so this gives minus k squared, and here it's a plus c sound squared k squared, and the exponential is contained both in this term and this term, so it cancels. So we are left with a so-called dispersion relation. A dispersion relation is a relation of the frequency, the eigenfrequency, and this here is, so to say, a wave number. K has the character of a wave number, so the relation between the frequency and wave number or wavelength is called a dispersion relation. So we have a relation between omega squared and k squared, and we can solve this dispersion relation for the value of the wave number k. We see this is a quadratic equation, and it means we have two solutions, and we can write down the solution explicitly. K squared is omega squared over the sound speed squared, and we have two solutions plus, minus, and k, because we have a quadratic equation. So the most general form of the solution of the one-dimensional the most general form of the solution, the spatial dependence of the solution would be v hat is an integration constant times e to ikx plus a second constant times e to minus ikx. What is it physically? What does it mean physically? This part of the solution, if you take in addition, if you add the time dependence e to ia omega, what does it mean? Plus k minus k, what does it physically represent? One, it's a wave going left and the other wave goes right. So these are two waves going in opposite direction. Now we apply the boundary conditions. The boundary condition at x equal to 0, then the argument of the exponentials is 0, and the exponential is 1. So the boundary condition at the bottom boundary of our organ pipe means that C1 plus C2 should be 0. Okay, let's take the the other boundary conditions at x equal to L, then we have 0 is C1 times e to ik L. L is the length of or the position of the top boundary, or is the length of our pipe, plus C2 times E2 minus IKL. If we consider, or if we apply or use that C1 is equal to minus C2, then we get a minus here, and we can cancel the integration constants anyway. So taking these two together, then we would have replacing C1 by C2, and then canceling or dividing by C2, we are left with 0 is e to IKL minus e2 minus IKL. Now we bring this factor here, and we are left with a small manipulation of this equation. We are left with e2 2 times IKL should be equal to 1. 1 in the complex plane is not unique. You know, in the complex plane, here you have imaginary axis and the real axis. You have the unit circle, and here you have 1, and you can represent 1 is e to 2i times 2p n, 2 pi n. Note to everybody, it's simple complex algebra, so we can write 1 is e to exponential of I times 2 pi n, and n can take on values 0, 1, 2. You can go round and round and round around the unit circle and get always 1, and you may represent it that way. So that means if you take the logarithm of that, well, it means that KL is equal to pi times n. And now inserting this again into our dispersion relation. So this means we have now found an expression for the wave number k. K can only take on discrete values discrete values given by pi times n over L. So you have our boundary conditions restrict the possible values of k. So that means the system is only solvable or has only a solution for discrete, of course, an infinite number of discrete values of the wave number k. K can take on values pi times n over L. Now using our dispersion relation, this means omega squared is related to k squared. This means omega squared, our eigenfrequency, is sound speed squared times the possible value of k, which is pi squared n squared over L squared. That means we have a solution of the problem only for discrete values of omega, and only then we can guarantee that we can satisfy both the boundary condition at the bottom and the top of our organ pipe. And the same will happen now for our star. The same situation happens for our star. We can have a solution of the problem, the solution meaning solution of the differential equation plus the boundary conditions, only for a certain number of eigenfrequencies, and the eigenfrequencies, so to say, are determined by the boundary conditions. So the eigenfrequencies are determined by the condition that we can construct a solution of the problem. This example, this analytical example, should make this a bit more intuitive, so that you know what you are doing once you are solving the numerical by a numerical scheme. You are solving this boundary eigenvalue problem for radial pulsations of a star. Is that okay? Does it help in understanding or getting some feeling what's going on? Here at the organ pipe is the same that's going on once we consider the solution of the perturbation problem for radial pulsations. Okay, you have to go through that step by step once again, but it can all be done analytically, and you can understand each step. And you can see how the solution is constructed, that two boundary conditions at each two boundary conditions distributed between the bottom and the top of the pipe will lead only to a solution in certain, or with only a solution for certain discrete numbers of the eigenfrequency. Okay. Okay, it tells you, you also get the solution. Well, the n equals 0 is the basic tone of the organ pipe. N equals 1 is the first overtone, 2 is the second overtone, and so on. Okay, solutions of the equation together with the boundary conditions do only exist for a discrete set of eigenvalues or eigenfrequencies. That's what we expect now also for our star. We expect a discrete spectrum of eigenfrequencies due to the solvability conditions, and we would like, of course, to know the eigenfrequencies of stellar pulsations. In this case of stellar pulsations, we do not only have a real part of the eigenfrequency, but we do also admit an imaginary part, which tells us something about the damping of a mode or about instability or excitation of a mode. Here, in that case, of course, it's a neutrally stable situation. In this case, the eigenfrequency is purely real. There is no imaginary part. These are neutrally stable oscillations of an organ pipe. Okay, there is one point left here, one issue we haven't considered yet in our equations, which is due to one of the coefficients of our system. Well, so far we have discussed the coefficient C3. This describes the stratification of density. Then the C4 is essentially a ratio between the sound speed squared and the gravitational potential energy. So that needs to be somehow be reflected in the coefficients of the perturbation equation, because these are sound waves and they have to be controlled by the stratification of the sound speed. There is one additional coefficient which we have not yet been considering. Well, apart from the 1 over r squared divergence of C1 and C4, all these coefficients C3 and C4 are of order unity. The only coefficient which deviates from that is the coefficient C1, and we need to consider this coefficient C1 a little bit more in detail. Let's go back to the definition of this C1. This actually varies a lot within the star. C1 is here. Here it is. So it contains, well, these two contain only mechanical quantities. This is the sound speed squared. This is clear that this must be reflected in the coefficients. But this coefficient obviously contains also thermal quantities. In the first place, it's the luminosity, and then also one coefficient of the equation of state. The delta is contained in this coefficient C1. Okay, let's consider what this coefficient C1 really means, how this can be interpreted within physical terms. Okay, and to do this, we first consider the thermal and dynamical timescale in a local sense. So far we have considered the dynamical timescale and the thermal timescale of a star in a global sense. That means we have taken the entire star to define either the dynamical timescale or the thermal timescale. Okay, so let's consider now, let's split our star into mass shells, and we would like rather than considering the entire star for defining dynamical and thermal timescale, we consider now a mass shell within our star, which extends from R to R plus delta R. Well, how could we define dynamical and thermal timescale on the basis of a small piece of our star? Well, one way to define the dynamical timescale would be to ask what is the fastest signal which we can have in a star. This is a sound wave which crosses this mass shell of thickness delta R. So the dynamical timescale would be the sound travel time across our mass shell of thick delta R. Sound speed is given by sound speed squared is the ratio of pressure over density. Well, these estimates are only order of magnitude estimates, so numerical number of the order unity. Okay, the time for a sound wave to cross would simply be the distance which we have to cross divided by the sound speed. So the dynamical timescale can then be defined by delta R, which is the thickness of the shell, times or divided by sound speed, which is the square root of p over rho, or divided by means the square root of rho over p. Okay, what would be the thermal timescale of this shell? Well, similar to the thermal timescale associated with the entire star, we could define it as the time needed to radiate away the thermal energy content of that shell at the local luminosity. So what we have to do is we calculate the energy content, the thermal energy content of that shell, and divide it by luminosity. Then we have the time this element needs to radiate away its internal energy. So we have to calculate the heat content of this shell. Well, the energy content is given by the specific heat times the temperature times the mass of the shell. Okay, now we replace the delta M by the density and the volume of our element. So the delta M, the mass in our mass shell, will be of the order of density times the volume. And the volume of a spherical shell is the surface of the shell, 4 pi r squared times delta r. Okay, now we have two timescale, a dynamical timescale for our mass shell and a thermal timescale for our mass shell. Defined now not for the entire star, but for a single or thin mass shell within our star. Okay, well, the question is, are these two quantities well defined? Okay, these are ill-defined quantities because they depend on the quantity which we cannot determine, which is arbitrary. So these two timescales are, in that sense, they are arbitrary because the delta R is contained in both of these timescales. But if we take the ratio of these two, then the delta R will cancel and we will end up with a proper definition, but not on the dynamical timescale and the thermal timescales themselves, but only on the ratio of both. So in a local sense, the dynamical and thermal timescale are ill-defined if they're taken separately, but if you take the ratio of these two quantities is well-defined quantity. So let's go to the ratio of dynamical and thermal timescale. dynamical and thermal timescale depend on delta R, and we have a well-defined quantity which is the ratio of thermal and dynamical timescale, which is given then by the ratio of the quantities I have shown before. This is a well-defined quantity. Please keep that in mind. There are authors which use these locally defined thermal and dynamical timescales separately, and they adjust the thickness of the shell according to their needs. This is not the right way to do it. You have to have a well-defined quantity, and this is only the ratio of these two. Whereas for the entire star, of course, we know how big the star is. There is a unique length scale which we should associate it with. This is the radius of the star. In the global sense, you can define both both timescales separately. They are well-defined quantity because the radius of the star is, of course, well-defined. But within the star, in a local sense, the delta R, the thickness of the shell you should take, is not a well-defined quantity. So this is well-defined, and it gives the ratio of thermal and dynamical timescale. And once we now compare this quantity here, once we compare it to the coefficient C1, which appears in our perturbation problem, then we will find that the essential dependence of C1 on, say, the radius or the mass coordinate is essentially given by this ratio. So the coefficient C1 reflects the run of the ratio of thermal to dynamical timescale. Let us perhaps at this position give some. So in general, this ratio is small, close to the surface of the star, and it increases once we go into the star. And I would like to give you some examples for the run of the ratio of thermal to dynamical timescale. Here we have two stars. We have this ratio, the logarithm of this ratio, thermal to dynamical timescale, for two different stellar models. One of them is a Cepheid, and the other one is a hydrogen-deficient carbon star. Well, it is written as log 1 minus x. X is the relative radius. So we have the surface of the star is over here, and the center of the star is here. What you see in any case, what happens also in any star, this ratio of the thermal to the dynamical timescale increases by orders of magnitude once we go towards the center of the star. And once we approach the surface of the star, of course, here the surface or the region close to the surface is expanded by this representation. So actually, this is a much smaller domain. But to expand this regime where the ratio of thermal to dynamical timescale is low, we see here close to the surface, this ratio is of order unity for the Cepheid, or it's even below order unity for the hydrogen deficient carbon star. Well, so in any case, deep inside the star, thermal timescale to dynamical timescale is large, and close to the surface, it may become of order unity or even less, depending on the stellar model. What does it mean once the thermal timescale becomes large? What does it mean? Pardon? Yes, that's true. If the thermal timescale becomes large, that means it takes a long time for the fluid element or for the mass element to exchange heat with its surroundings. That is the meaning of a large thermal timescale. So if we go inside the star, it will take a long time for the mass element to exchange heat with its surroundings, and that means heat exchange with the surroundings means adiabatic changes of state. So the star becomes, or the perturbations become, not the star, the perturbations become adiabatic once we approach the center of the star. And there are non-adiabatic or need deviations from adiabaticity need to be taken into account only close to the surface. And then we have to distinguish between stars where this region where the thermal timescale is small, or the ratio of the timescales is of order unity, where this region is small. This is for a Cepheid. So for a Cepheid, a large fraction of the star can be described by adiabatic perturbations, whereas for this hydrogen deficient carbon star, the domain where the thermal timescale compared to the dynamical timescale is low is much larger. In that case, we cannot expect that adiabatic perturbations are really a good approximation. So not for this one. And here the region is much smaller, where non-adiabaticity needs to be taken into account. This is for the hydrogen deficient carbon star. Seems to be further off the adiabatic limit than the Cepheids. Okay, let's give you another example. This is the run of this timescale for two massive stars with same effective temperature and same luminosity but different mass. So we have a high mass object. It's same luminosity and same effective temperature, high mass and low mass object. Again, you see here, close to the center, or always if you approach the center, then this timescale is large. So we have adiabatic changes of states here. Whereas once we go to the surface of the star, then this ratio drops below unity, either here for the 60 solar mass object at the outer 10% of the radii, whereas for the 24 solar mass star, it's of order unity or below in the outer 50% of the star. So this star will behave adiabatically more than the 24 solar mass, because the domain where the thermal timescale is high compared to the dynamical timescale is much larger than for the massive object. So it depends on how big the domain is where this ratio of thermal to dynamical timescale is of order unity or less. Okay? So these are the examples. And actually now this coefficient C1 is essentially this ratio, and therefore the thermal, or C1, is controlled by this ratio of the two timescales, the thermal to the dynamical timescale. So what is the consequence? Well, it means that the term in front of which, the bracketed term in front of which this coefficient C1 has to vanish. Okay, if we go towards the center. Let's go back to the equations once again. Sorry. Okay, this is the equation where C1 is appearing. If C1 attains very large values, well, take it to the other side. 1 over C1 is small, then L dash should be finite. Then this means vanishing of C1 means that this bracketed term has to become small. And what does it mean if this bracketed term becomes small? Well, let's consider the pressure as a function of temperature. And for instance, pressure is in general a function of temperature and may be written also as in terms of the entropy. Then dP, if the entropy is constant, then P is a function as constant. That means P is a function of T, or d log, or the if we use the if we express the the temperature variation in terms of temperature perturbation in terms of the pressure perturbation, then we have T1 over T0 is something like the T by the P at constant at constant entropy times P1 over P0. That's simply taking assuming perturbations of temperature and pressure, and so this is then this is P over T. So this is d log T by d log P at constant entropy, and this is the nabla adiabatic by definition. So this is in this notation, T is nabla adiabatic times P, and this is exactly what is meant by this bracketed term. So if this bracketed term vanishes, we have adiabatic changes of state. Okay, well, this was the time derivative of the entropy, and so what you see here, this is the deviations from adiabatic behavior, which is left once this bracketed term is not zero. Okay, so we know T is nabla adiabatic times P, and in the case of adiabatic changes of state, and in that case, this bracketed term will vanish. Then also, as a consequence, of course, then also the luminosity perturbations will vanish. There is no heat exchange with the surroundings, and therefore we don't have any luminosity perturbations. So another expression of constant entropy would be that this bracketed term is zero, or that temperature perturbations and pressure perturbations are related by the relation T is nabla adiabatic times P. Okay, so large values of C1 or large values of thermal timescale to dynamical timescale force that this bracketed term will become zero. As boundary conditions for are not equal to zero, because C1 diverges like 1 over R squared, we had that this bracketed term had to be zero as well. So just for regularity, this term has to vanish, but also if the coefficient becomes very large, then this bracketed term has to be close to zero. Okay, and this means we have adiabatic changes of state. So we have adiabatic changes of state for sufficiently deep layers. This is equivalent to the time derivative of the entropy becoming zero, or that the entropy becoming constant, or in other words, adiabatic changes of state. That means sufficiently deep in the star, pulsations are adiabatic. T is nabla adiabatic times P. This is the condition, the explicit condition for constant entropy or adiabatic changes of state. Okay, well, what happens if we have adiabatic changes of state? Well, if we have adiabatic changes of state, the consequence is that we can abandon, by this relation, we can abandon all the thermal equations. Because you saw, if nabla adiabatic times nabla adiabatics T is equal to nabla adiabatic times P, then we also lose the luminosity perturbation. No heat exchange, no luminosity perturbation. So if we have no luminosity perturbation and the temperature is directly related to the pressure, then we can decouple the thermal and the mechanical equations. We can ignore the thermal equations because one of them is anyway satisfied. This is the energy conservation, and the energy transport is no longer needed because luminosity is zero. So What happens to the remaining mechanical equations? I have to go back here. Once we explicitly require temperature is nabla adiabatic times P, well, let's go to the equation once again. What we are left with is then, well, this equation is satisfied. Luminosity perturbation is 0. This equation is no longer needed because luminosity is gone. Well, there's only one place where the temperature is appearing here. Temperature appears in the mass conservation equation at this place. Now we know that temperature perturbation is given by the pressure perturbation is nabla adiabatic times P. Then we replace the temperature here by the pressure perturbation, and then we have the system decoupled. So the upper two equations do only contain the zeta and the P and are decoupled from the rest. So we can consider these upper two equations by themselves. The system is decoupled once we have adiabatic changes of state. And there is a transition to the full problem once the C1 is no longer infinite but has finite values, or once we consider the outer layers of a star. Okay, so we're left with a much simpler system describing adiabatic perturbations. Okay. In that case, we have the following. Okay, mechanical and thermal equations are decoupled and only the mechanical part is left. The first one is the mass conservation, where we have replaced the temperature by nabla adiabatic times P. And the second one is unchanged, which is the momentum conservation, containing the remaining place where the eigenfrequency sigma appears. This is the acceleration term. So we are left with a second order system once we require adiabatic changes of state. Again, we need boundary conditions for this system. These are the boundary these are now two boundary conditions because we have a second order system. There is again or remaining the regularity condition, which was present in the previous case. Just that in that case, well, C1, C4 goes like 1 over r squared. So for at the center, this bracket term has to vanish. This is the analog of the previous regularity conditions, 3 theta plus alpha minus delta nabla adiabatic, which comes from the adiabatic changes of state. P times P is equal to 0. And we have to have one boundary condition left from the surface, which of course then would be the condition which requires a force-free boundary. So we have second order system, two boundary conditions, and again the frequency, the eigenfrequency as a free parameter in our differential system. Well, this is the case once C1 becomes pretty large. We could also go the way and say what happens if we require adiabatic changes of state over the entire star as an approximation. We know it's only an approximation because in any star the ratio of thermal to dynamical timescale becomes small close to the surface of the star and it increases inwards. So for the entire star, it's certainly not a valid approximation. The question is to which degree will it be a reasonable approximation? For the Cepheid, it might be a reasonable approximation because the region where the thermal timescales are small and non-adiabatic effects have to be taken into account. In that case, this region is small and the adiabatic approximation taken for the entire star may be a valid approximation. Not for the hydrogen deficient carbon star, where we saw that 50% or even more of the star is characterized by a low thermodynamical timescale. Well, if we assume this adiabatic change of state for the entire star, of course, then this system would be valid for the complete star, and we could try to solve this system independently of the full non-adiabatic equation and see what the results will be. Okay, so these are at the same time not only those equations to which the general equations reduce in the case of getting close to the center of the star, but these are also the general equations for adiabatic, for the assumption of adiabatic changes of state, or this is the adiabatic approximation. These are the equations of the adiabatic approximation for adiabatic pulsations and adiabatic perturbations, adiabatic linear radial adiabatic pulsations and stability of a star. So at the same time, we have now derived this approximation, which we shall deal in detail later on. So this is one of the valid approximations, or one of the possible approximations to the full non-radial, to the full radial non-adiabatic problem. So this is the reduced form for radial adiabatic pulsations and stability. Okay, I think now we are finished with the radial stuff, and in the next lecture we will start to consider non-radial perturbations around a spherically symmetric hydrostatic model. So see you. You say it's time. Okay. So next lecture we will go to the non-radial case.